Welcome back. So, where are all these pesky volcanoes that I just spoke of? Well, let's find out, shall we? Okay, so most volcanoes are near plate boundaries. Not all, just most. More on that in a minute. When we're talking about volcanoes, this is a place on Earth where material comes out, some of that being magma. So if we're talking about where does most of the magma come from? Well, actually, magma, the molten material from below ground, that's kind of melted somewhere between the upper mantle or up into the crust, most of that comes out at mid-oceanic ridges, at places where oceanic crust is diverging from one another. So a divergent boundary underneath the water. That magma material is kind of moving up, filling in that gap, and that's what's creating new oceanic crust. So 75% of the annual output of magma on Earth comes in these areas. However, the sheer number of volcanoes and active volcanoes are most likely found around convergent boundaries. And in fact, approximately 2/3 of all active volcanoes are found within the Ring of Fire. The Ring of Fire is kind of a fictitious zone around the Pacific Ocean that, more likely than not, you're looking at convergent boundaries in these areas that creates so many active volcanoes. So 2/3 of all active volcanoes on Earth are surrounding the Pacific Ocean. Not just the Pacific Plate, but the Pacific Ocean. So here's another kind of look at a map of volcanoes. The red triangles are volcanoes. Again, most volcanoes you're going to find near plate boundaries, but not all. For example, look at Hawaii, out here in the middle of a plate, nowhere near a boundary. This little triangle over here, this is Yellowstone, not really near a boundary. What's going on? What's going on with these places? Look at some of these places, for instance, like in Africa, really not near a boundary as we know it. So what's happening? What's going on here? Well, not every volcano is the same. A lot form from convergent boundaries. The I's and C's indicate areas where you would get these volcanoes formed by convergent boundaries. So island arcs are formed when oceanic crust converges with oceanic crust. Continental arcs are created when oceanic crust converges with continental crust. So I's and C's you can see all around the Pacific Ocean around this Ring of Fire. But you do have areas that are rifted, so kind of being ripped apart on continents. For instance, what's happening on the Basin and Range Province, how Arizona formed, what's happening in the Great Rift Valley in Africa. If we're looking at kind of that same divergence but underneath the ocean, we'd be talking about a mid-oceanic ridge. There's no M's on there, but really any of these would probably be mid-oceanic ridge, divergent boundary, volcanic activity. And then H is for hotspot. So again, most volcanoes happen near a boundary. But again, look at Hawaii, way out here away from a boundary. It's over what's known as a hotspot. More on that in a second. Iceland, hotspot. Yellowstone, hotspot. Lake Nyos in Cameroon, over a hotspot. So again, most volcanoes near boundaries. Some aren't. And some of those include these things called hotspots. So hotspots are just kind of mantle plumes, so plumes of hot convected mantle material that are just, for some reason, hotter than the surrounding stuff. So you got this area of hot upwelling mantle material. A hotspot develops over that kind of plume. So you have, for instance, some upwelling of hot mantle material, and then above it, it's melting that crust, for example. So it's melting that crust, turning it into a magma. So that magma is generated by the heat from the hotspot. That magma rises through the crust and produces active volcanoes on Earth's surface. What's interesting to note is that hotspots stay in place, but we know the plates move over it. So you can actually get a series or a string of volcanoes as a plate is moving over a hotspot. So you get a plate moving over a hotspot, volcano. Then the plate continues to move, another volcano. Plate continues to move, another volcano. Which is what is somewhat illustrated here. So this is volcano 1. As that plate motion continues, there's really nothing pushing it up, so it kind of subsides a bit, but creates another volcano. Plate continues to move, another volcano, plate continues to move, another volcano, etc., etc. this is how Hawaii was formed. So the islands of Hawaii, the 5 main islands of Hawaii, are on the Pacific plate, and that Pacific plate is moving over a hotspot. So the oldest of the Hawaiian islands is Kauai. The youngest of the Hawaiian islands, is Hawaii itself. So as the Pacific plate moves in this direction over the hotspot, each of these were subsequently created. But also, since now Kauai is no longer over that hotspot, that volcano is no longer active. The remnants, the mountains and the lava flows of when that did occur, means the island is around, but it's not volcanic anymore. What's interesting to note about Hawaii is if you look at the ocean surface, it's not just a handful of Hawaiian islands. Below, we see actually a whole string of them that have subsequently been weathered, eroded, and subsided. So we see a whole string of islands on the surface floor that were created by the Pacific plate moving over this hotspot. We can actually see that the Pacific plate actually kind of changed directions. So in this case, the Pacific plate was kind of moving more northward over the hotspot, and then all of a sudden, it kind of shifted off to the northwest. So it's indicating different motion. All of these created as it travels over some massive hotspot below the Pacific plate. Again, here's another look at it. Imagine this kind of mantle plume creating this hotspot right over it, which is now Hawaii, but it was under all these other islands as it kind of had moved over. The Pacific plate had moved over this hotspot. But that's the reason why we have volcanoes like Mauna Loa and Kilauea. So in some time, we'll actually probably have a brand new island as this hotspot activity continues. Where else around the U.S.? So obviously Hawaii has volcanoes. There are a decent number of volcanoes in Alaska, most along that long arm of Alaska that jets out into the Pacific Ocean. These are known as the Aleutian Islands. The reason that these are all volcanic because we have a convergent boundary here between two oceanic plates. So you're creating a lot of volcanoes on that island arc. And then as far as in the lower 48, we still have plenty of volcanoes around. Mostly along the west coast, but we do get some all the way over into Wyoming, Colorado, New Mexico as well. But nothing else really past that. So mid-America, East Coast, no volcanoes. So where are the volcanic hazard areas? It doesn't really include those islands in Alaska because really little to no people live out in some of those areas. So there's no hazard there. It doesn't include the state of Hawaii here because a lot of those flows are gentle, slow-moving flows, and they can cause property damage, but not so much hazards to life. When we're talking about those, that's more associated with, unfortunate for us, the volcanoes we have here on the kind of the west coast. Because of that convergent boundary, subduction zone, the kind of magma, the andesitic magma, which is kind of a medium viscosity, sticky, volatile, explosive content, creates these volcanoes that tend to explode quite fantastically when they erupt, causing a much bigger hazard. So red is the high volcanic hazard, pink kind of the lower. When these types of volcanoes do erupt, they do emit a lot of ash, and ash can provide in itself a hazard. More on that a little bit later in lecture. But you can kind of see the affected the areas that could be affected due to volcanic activity. And again, in Arizona, we are not safe, I guess, from volcanic hazards. We have plenty of volcanoes right here in Arizona. Ooh, segue. Why is that, you say? Think back to how Arizona was formed. Plate tectonics kind of ripping on Arizona, thinning and stretching out the crust and the mantle material. As that crust is thinned and stretched out, mantle material is kind of pushing it up, cracking it, causing the basins to drop, the ranges to rise, normal faulting. But in doing so, in creating all these cracks, you're giving an avenue for material to kind of make its way through, or when you crack the ground, you're giving a pressure release avenue for any volcanic activity below. Excuse me. So remember the basin and range formation that began, between 10, 20, 30 million years ago, but really focusing around 17 million years ago. That's when the bulk of this basin and range extension, this tectonic extension occurred. This plate thinned, allowed for magma to rise to the surface in some locations. So when we're looking at a distribution of volcanic rocks in Arizona, we got plenty of them. There are plenty of them. So looking at all these different colors indicates different area or different volcanic areas through time, going back about 200 million years. So the green and the blue, not so much, but as you can see, as we get into the yellows, oranges, and reds, a lot. And a lot of that's tied to that basin and range province formation, which kind of, was at its peak around 17 million years ago, but still ongoing today. So that's why you get a lot of yellows, oranges, and reds. So if you're in the Phoenix area, you don't have to go too far to find some volcanoes. Head to the west, over near Buckeye. Head to the east, out past Mesa. Head north, up to like Black Canyon City. You don't got to go far to find volcanoes in Arizona. Now, none of them are active. They are either extinct or very, very dormant, meaning they're not coming back, or the likelihood of them coming back is very small, but they're there. So on that scary note, let's go ahead and pause here. When we'll come back, we'll talk about the different types of volcanoes, and that's dictated by the type of magma that is created to create these volcanoes, and the different eruption types that occur from the different types of magma. So again, we'll pause here, and I'll see you back here in just a second.